Hey, good morning, everyone. Welcome to HPC in the Cloud. I am Joe Schoonover from Fluid Numerics. Thank you for joining us. Today, we're going to be talking about Python package management strategies, particularly on HPC clusters. We're hoping that this is useful for both administrators and HPC developers. You know, as we move forward, cloud computing is putting HPC resources in the hands of more and more people, and we're seeing that there's a need for I guess just more skills in our toolkits these days as HPC developers to keep pace with what's coming our way and to take advantage of these awesome resources. Just some prerequisites if you're going to be following along with the tutorial. We'll be using an HPC cluster that you can click to deploy on Google Cloud. So if you want to follow along with exactly what we're doing, you can start by going to console.cloud.google.com, create an account. If this is your first time on GCP, you'll get some free trial credits for that, to which you can put towards this tutorial. And then the other bit here is just to get yourself started, go ahead and create a Fluid Slurm GCP cluster. I'll give you a quick overview of how to do that. If you do check out through our previous videos from live streams from a couple weeks ago, we do have a very extensive tutorial on how to get that off the ground, but I'll give you a quick start here. Once you're in your cloud console, you can go to the products and services menu up in the top left, go down to marketplace, search for Fluid Slurm GCP, and just go ahead and use that first resource there and then hit launch. There's just some very basic entries, values to fill out here to create your cluster. The most important one I'll point out to you just for today for the tutorial, you don't need 64 vCPUs. Oops, looks like my console disappeared here. Let me get that back up for you. There we are. When you're on that page, so again, we went through products and services, hit Fluid Slurm GCP from the marketplace, click through, hit launch, and then down on this form here, the most important thing here for today, we don't need 64 vCPUs for the compute partition. So you can just go ahead and select 2 virtual CPUs just by hitting that drop-down menu, and make sure you slide over to N1 standard 2. And that should do it. Once you're done, hit launch or hit deploy. I've already deployed one for this tutorial already. When you're done deploying, it will bring you to a deployment manager page that looks something like this. By the time your cluster's done, you should see a login IP address and a controller IP address. And the quickest way to get started, go ahead and click that SSH button. That'll drop you in the login node in a terminal in your browser. So that's really it on the prereqs here. I'm going to try to figure out why my slides are not updating either. Give me one moment. Okay, there we go. Weird things are happening this morning. Little technical difficulties, but we're back on track now. So what we're going to do today, right, is go through Python package management strategies. Again, particularly for HPC clusters, we're going to demo this on our click-to-deploy solution on Fluid Slurm GCP. So we're going to look at 3 different ways to do this. What I call a centralized approach, which is where we're going to install Python, Python itself and Python packages on an NFS-mounted directory that's available to the login node on this on a cluster and to all the compute nodes that you can access through a job scheduler. And then we're going to look through a decentralized approach, where this is these last 2 strategies, really both decentralized and containerized, are methods that put the package dependency management for software, for HPC applications, for deep learning applications, what have you, in the hands of in the hands of the developers. Neither of those methods really require root in the way we're going to show you today. On the decentralized approach, we're going to be looking at virtual environments with Python. And on the containerized side, I'm going to show you how to use Google Cloud Build to create Docker container images, and then to pull those images into a cluster. If you have Singularity there, you can pull those images in, create Singularity image files, and launch those without having to go root. So let's go ahead and get started. We provided a demo repository for this tutorial that you can use to follow along. Of course, if you have your own code, you can follow some of the steps similarly with your own code. But if you want to use that one just to follow along with us, you can do this git clone on our GitHub repository. Under fluid numerics, you can find the fluid slurm GCP Python demo.git. Now you're going to need this in two spots. You're going to need a copy on your cluster, and you're also going to want a copy on your local on your local system. The reason why you want it on your local system is actually we'll be running Google Cloud build from that system. Now, if you don't have the gcloud SDK already on your local system, you can use the Google Cloud shell, which you can actually get to from the Google console. So if you look on the top left here, on the Google console here from the deployment manager page, really on any of the pages, up on the top right, there's a button that you can use to activate what's called the Cloud Shell. And that Cloud Shell will open a terminal in your browser. You can pop that to a new window if you'd like. And this will have the gcloud SDK already set up, ready to go for you. So if you want to do this in Cloud Shell, you can use git clone, because Git's already on here as well, to clone that repo onto the Cloud Shell. Now today I'm actually going to be using my own terminal because I do have the gcloud SDK set up. So that's really it. I'm going to go ahead and close that out. And like I said, I do have that Python demo slurm GCP already locally. But let's go ahead and hop into our compute nodes. So I'm going to go to the compute engine page. You can get to that through the from the products and services menu. Click on that triple bar menu, go down to compute engine, and you should see a page that looks like this once it starts loading. Once it ends loading. So we have the login node and the controller. I'm going to copy that IP address. I'm going to go ahead and SSH into that. Now I've set this cluster up before I got here, but you'll also, like I said before, make sure you have a copy of that repository here as well. So here we have fluid slurm GCP Python demo. Let's take a look at what's inside. Outside of that CIF file, that was from last night's tutorial. So let me go ahead and kill that. So we have a few things in this repository. I'll briefly go over them. So we have cloud build YAML and a Docker file. Those are going to be used for the containerized approach, so we'll talk more about those when we get there. There is a script available if you do want to install Python in a non-standard location on your own system. There's a script here that enables you to do that. And we'll talk more about this requirements.txt in this env directory shortly. There's also some batch files. So basically, we're going to be test running our application using Slurm batch jobs as we go through. And the application that we're going to run is this test.py. So let's take a look at what's going on inside of there. So this application, all it does is it imports SciPy, NumPy, and Matplotlib, and then it will actually just print out the version of each of those libraries, and then print out the path to those libraries. And the reason why this is important is just to illustrate to you guys, as we change the different strategies, the locations where those packages are available will change with it accordingly. And we'll see this happen along the way here. I'm actually going to go ahead and clear this env directory. So we'll start fresh today. You probably don't have that if you're starting fresh from the repository. I guess it's a little sloppy here in cleaning up from yesterday's tutorial. But that's all right. So the first thing we're going to do, let me go ahead and advance to the next slide here, is this centralized package management. And so essentially, when you're on, at least on the Fluid Slurm GCP cluster, and this is very similar for most HPC clusters, is you'll have certainly home directories, and then maybe some shared working space directories that are NFS mounted to all the other the other computers in that network. So for us, we have a login node that's basically, we have the controller, which is hosting apps in home to the login node, and it's also being brought up on the compute nodes when those compute nodes come online. So if I wanted to have Python available on all those compute nodes, and I wanted to have the Python packages associated with that Python install available to compute nodes, I have to use something that's NFS mounted. So let me illustrate this a little bit. If I were to run which Python 3 and which pip 3, right now it's referring to the system installs for Python 3 and pip 3. These are under user bin. Now, since I'm on the login node, this is user bin on the login node. Those directories, although, yeah, the compute node has a user bin directory, the controller has a user bin directory, it's not the same, it's not going to be the same instance of that installation elsewhere. So if I were to use this pip3 to do package installation, they will not be available on the compute node simply because there's no mechanism right now to share user bin from the login node to the compute node. So we have to go through this route of using some location in Homer apps to expose those packages to the compute nodes. And again, that's simply because those are the only directories that, at least on our system, and I'm sure on a lot of other HPC clusters, you'll have a similar setup where there's only a small set of directories that are actually NFS mounted to the compute nodes. So the first route here is we're actually going to use an installation of Python underneath apps, which if you're using our system, we make that available through environment modules. So if you run module avail, you'll see that we got Python 2, Python 3, and we do have Singularity, which we'll be getting to towards the end of this tutorial today. We're going to work with the Python 3 module. Now, in order to install anything under apps, and certainly on a lot of HPC clusters where package management is handled by system administrators, a lot of these directories are going to be root protected. So this strategy is really recommended for groups who want to have a centralized sysadmin team who want to do the package management for the researchers and let the researchers kind of just work on deploying their applications, doing their research. So to do this, to go this route, you will need to go root. So go ahead and hit sudo su, and then once you're root, go ahead and module load. We're going to do module load Python 3.8.2. Okay. So now if I run which Python 3, you see now it's referring to the Python 3 underneath apps, and if I run which pip3, it's also referring to pip3 underneath apps. Now the way Python works is wherever that installation is that we're referring to for pip3 and Python 3, underneath those directories, so if I were to look under apps, Python 3.8.2, okay, I've got bin include and lib. Underneath the include and lib directories, when I install packages, those packages will be placed there. Basically the header files and then the actual libraries themselves. Right? So the deal is if I were now to run pip3 install scipy matplotlib and numpy, what's going to happen now is all those three packages are basically going to be installed under apps. So I did these yesterday, so they're already here for us, which is great. So that goes through pretty quickly. So now when I actually, if I were on a compute node and I did, hey, module load Python 3.8.2, I can actually now take advantage of those packages because they're basically brought in from that apps install, which again is NFS mounted to those compute nodes. So to test this out, go ahead and get out of root. Okay, we do have a test batch file for you. So let's take a look at test.batch. This is a Slurm batch script. It's divided into two sections here. The top half is what we call the Slurm header. And as you can see from the shebang at the top, it's just a bash script. But it's got some special commands for interacting with Slurm's sbatch command. The most important things, most systems use Slurm accounting, so if you're using these scripts to follow along, make sure that the Slurm account matches the account that you're set up with on your system, and make sure the partition is also set up correctly to the partition you want to submit to. Now down below, all we're doing is we're cleaning up modules just in case there are any existing modules previously loaded on that compute node for my account. Now you'll do a module load Python 3.8.2, and what we're going to do is just run which Python 3 again to confirm that we're using Python 3 underneath apps, and then we're going to do Python 3. We're going to run test.py. And what we should expect to see is that it's basically going to report everything Python 3 and all the packages existing underneath apps. So let's go ahead and run that. So you'll just do an sbatch test.batch. Okay. If you look at SQ, what we've got is a job that's configuring. In the demo partition, we're using demo partition 0. And if I were to run an sinfo, you can see that demo partition 0 node in the demo partition is allocated. Now that pound sign just means it's in what's called a power up state. This gives me an opportunity just to kind of introduce for you what I mean by an auto-scaling cluster. For the FluidStorm GCP deployment, essentially what happens when you submit a job, if the compute nodes aren't actively available, what's going to happen is the Slurm controller is actually going to go and create those instances on Google Cloud for you. It's going to run the job, and then after 5 minutes of that node being idle, it will take it down. Now, the nice thing is, once that node's up, if you are actively continually submitting jobs, you really will have no queue time. So for this first round here, while we're waiting for this node, that whole spin up process essentially is, okay, we're going to issue a call to create the instance. It's going to create the instance with an image that we've provided for all of you as part of the FluidStorm GCP cluster. When that node comes online, the startup script sequence basically is, all right, we need to mount home and apps. We need to initialize a Slurm daemon. If you're running on GPUs, it's going to initialize GPU drivers for you. All that stuff's already taken care of. So this process can take anywhere from 30 seconds to 2 minutes. I think yesterday we had a pretty fast turnaround. So we'll see what happens here. We're at about 1:36 so far. Let's refresh on the console. Looks like that node's ready, so it's probably finishing up that startup script very soon. We'll keep an eye on this. Yeah, so let's go. I guess we're just going to have to wait for this to come. Oh, perfect. It already ran. So let's open up that test.batch real quick. I just want to point something out. That -O and -E flag, they stand for basically the locations where we want to. It's an option to tell Slurm where to pipe the standard error, standard output for -O, standard error for -E. We're going to put those in test.out. So if I look at test.out, okay, what we've got is which Python. Like I said, it's going to be the one underneath apps, and it did find the Python underneath. The SciPy, NumPy, Matplotlib, also underneath apps. Let's just try something just to illustrate why this is important again. So if I were to remove, let's remove that Python module, and let's just say I'm going to say module purge on this side as well. Let's just say I did do pip3. So first, which pip3 are we using? I'm using the user bin pip3. So pip3 install SciPy, Matplotlib, and NumPy. There's no package name and. Come on. Actually, I'll need to be root to do that because it's going to install underneath user bin. So I'm just going to demonstrate for you here why we have to go this route to where we're using an NFS mounted location. So what I'm doing right now is just basically installing these packages underneath user bin on the login node, and then we'll rerun that job without the environment modules. And basically what I'm going to show you is we're going to get a failure. So if I were, again, go back to that test.batch, all I've done now is purge the modules. I'm not loading Python 3 now, and I'm running which Python, and I'm going to run test.py. So let's do that. Because the node's already ready, it's going to go right through. Cool. Let's take a look at test.out. Okay. Can't find SciPy. So this illustrates, I hope, for you guys, like why we have to do this sort of, it almost feels like sidestepping, but why we have to do the package installation on an NFS mounted location. All right, so enough with that. Let's move on to the next strategy here, which is the decentralized approach. We're going to use virtual environments. This is a strategy that's great for Python software developers who want to have more control over the packages that are available to them. And you don't need to do it in a root location. They can do it in their home directory. You'll still, if you're using our cluster, want to use the Python 3.8 module, but you'll use it as yourself, not as root. So let's go ahead and module load Python 3.8.2. And what we're going to first do is basically use the VNV package, so virtual environment package, Python 3. We're going to use the Python 3 virtual environment package to create this local directory called env. And that local directory for env is going to basically replicate the directory structure that we saw underneath apps Python 3.8.2. So we got a bin include in a lib. Okay. So if I were to activate this virtual environment, whenever I call Python 3, whenever I call pip3, it's going to reference Python 3 and pip3 that are available in that bin directory. Okay, so you see we've got basically Python 3, which is really just a symbolic link back to the original one. We've also got a pip3. So how can we take advantage of this? Let's go ahead and activate that environment. Okay. And now you'll notice on your shell prompt you have an env in parentheses on the left-hand side. Let's go ahead and just take a look again. Which pip3 are we using? We're using now pip3 in our home directory, just like I said, and then the same thing with Python 3. Okay. So let's do a pip3 install. You'll notice that I'm not using sudo anymore, which is kind of nice. So we'll go ahead and let this install, and we're going to do the same thing next. We're basically going to run through a batch job script that's going to test out basically using the virtual environments to run our test application. Now, there's another cool side effect here of using virtual environments is pip3 has a function called freeze that will basically report out all the packages and the versions that you're currently using for your application's development. And you can actually dump that information, all those packages that your application depends on, into a file. And usually it's called requirements.txt. So if I were to do pip3 freeze, and just to show you what comes out from that, right, it's gonna have all the packages that got. Now I know we just said matplotlib, scipy, and numpy, but those packages themselves also have dependencies, which is why we see other packages here. If I were to say pip3 freeze and forward that output to a file, usually it's called requirements.txt. All right, so if I take a look at requirements.txt, all the same packages are listed there. And nice thing is, if you want to share your code now with someone else, basically add this requirements.txt file to your repository, and then give them the same instructions for getting started with your applications. You'll have them, when whoever your users are on another system, basically run through the enablement of virtual environments. So they'll run that Python 3 -m, etc. They will run source env bin activate, so they'll create their own virtual environment, and then they can just run pip3 install -r requirements.txt. So they don't have to write out every single package that your application depends on, but you can basically, hey, here's your 3 steps to get started. Your application ends up being portable, pretty nice and clean. This also, again, when you're on an HPC cluster in a shared environment, and you might not have the capacity on a system administration team or what have you, or maybe it's just a better decision for your organization, for your developer team, to just say, hey, look, we're not going to have you guys go root. It's not really necessary. Let's go ahead and just do it this way. This is a great strategy. Let's take a look at how this changes the batch file. So when you go to run your job now, you're still loading Python 3.8, but now, before you run your job, you'll need to activate that virtual environment on the compute node. So you'll run that source env bin activate. And again, we're going to run the same commands we did before, which Python, and then we're going to run our application. And when you're done with your virtual environment, you can just hit deactivate. So let's go ahead and do that. Hopefully I didn't wait more than 5 minutes here between jobs. So this job should go right through, and it did. Great. Let's take a look at that test.out. All right. So which Python? It used the one underneath my home directory. In fact, the one underneath the env directory in my current working directory. Same thing with the scipy, numpy, and matplotlib libraries. Pretty cool. All right. So let's get to the last strategy here, which is the containerization approach. So it might feel like there's a few more steps here, and there kind of is, but once you get into this workflow, it can be highly productive for a lot of teams. Essentially, this containerized workflow that I'm going to introduce to you guys is basically going to separate out your development process and your deployment process. So if you're thinking about, man, well, it would be great if I could just develop my applications on my own system and not have to pay for compute nodes to be constantly running, etc., you can do that. We actually do that quite a bit at Fluid Numerics. Applications that we develop, we build in-house on workstations, submit them to Google Cloud Build to create containers. And then for our HPC applications, we actually use Singularity on the cluster to pull those container images, which are natively in Docker. We could pull those in with Singularity and run them on the HPC cluster. So I'm going to go ahead and log out from the login node. I'm back on my local workstation. Okay, and what we're going to do is open up two things here. Let's take a look at the Docker file that we have. So the Docker file is simply a recipe to install your application. Now this one's very simple. Certainly other applications will have more dependencies, especially if you're in HPC. I'm sure you're familiar with trying to build like HDF5 and NetCDF stacks. It ends up being quite a bit to put in a Docker file, but it is doable. But the idea here is basically let's give ourselves a clean environment every time we can build the application here. And then, so what this does is it just runs through pip3 install for our dependencies, and we can copy basically the whole current working directory on our host system into a directory in the container called app. And then the other file here, which is the file that interfaces with Cloud Build, is cloudbuild.yaml. This was essentially a YAML dictionary that tells Cloud Build the steps it takes to build your application. We won't be going into a whole lot of detail on Cloud Build today, just enough to get you through this Python package management stuff. But if you join us in a couple weeks here, actually both next week and 3 weeks from now, we'll also be doing we'll be diving into a lot more stuff on Google Cloud Build for creating virtual machine images, for container images, etc. Definitely subscribe to our channel and to keep up on what we got coming for you. So anyways, this cloudbuild.yaml file, right now all it's going to do is call Docker, and it's going to build using our current working directory, and it's going to publish that image to gcr.io, which is Google Container Registry, for my current project, and it's going to name that image Python demo slurm GCP. So let's go ahead and create that image. So you will need gcloud SDK to do this. We're going to run gcloud build. I think it's builds. Well, let's go to the next slide. Sorry, I didn't advance that. We're going to do gcloud build submit, and we're going to use the current working directory to do that. All right. So what's happening here when you run Google Cloud Build is in the back end on GCP, there's an isolated environment that's created to do your whole build process. You won't be able to access it. It's highly secure. Now, if you're doing manual triggering like this, you'll see the logs come out on screen. Of course, let's go ahead and dive into that Cloud Build panel. So if you go to that products and services, you'll need to go down underneath tools. I like to pin commonly used tools. So if you were to hover over some of these, you'll see a pin button. And it'll bring it higher up on your menu. What you'll see if you don't have triggers configured already, it's just going to show you a history page of all the builds in this project. With pass-fail, and of course if you click through, you'll see those same logs coming through, and you can search through execution details, build artifacts, and all that. Now this whole system also has an API for Python, for Java, etc. So if you wanted to tie this system into other platforms, you can certainly do that. Now Cloud Build through triggers does natively interact with Bitbucket, GitHub, and Google source repositories, so that you can set up triggers on pushes to branches, tags. And if you're using GitHub, you can actually control builds based on the opening of pull requests, which is kind of nice. We won't be talking about triggers today. That'll be subject for a few weeks from now. So the basic thing here is what's happening is we've got this build happening in an isolated environment, and then from here, the image that's created, we open up that products and services menu again and go down to tools. You'll see container registry. It's going to post a Docker container image for the image we just built. So here you see we've got our Python demo, slurm GCP. And it's like any other container registry. You have multiple container images available, and you can do any of your tagging conventions. All of that stuff works here. Now in the back end, all those container images are actually housed in Google Cloud Storage, which means you can control who has access to those images through identity and access management policies. And all you need to do to give someone access to that resource is to give them storage object viewer role in identity and access management, and they'll be able to pull it. Now we've set up our cluster so that the login node and the controller, the compute nodes, all have access to be able to pull from that container registry for you. So again, if you're using the Fluid Slurm GCP cluster, we can move on to the next step of simply pulling that image onto the compute cluster with Singularity, and then we'll run it. So let's go ahead and get back into that login node. I guess I'll make the point that if you are on your own instance, there are ways to actually authenticate your own on-premise resources using what are called service accounts. If you're interested in learning more about that, you can reach out to us on the chat channel on this YouTube live stream. Just hit the subscribe button. That chat window should be open for you. We'd be happy to answer any questions you might have about setting that up on your own system. So let's go ahead, and I'm going to change directories into here. Now, the first thing you need to do on the really on any system is, if you have Docker installed and you have Singularity installed, you basically want to create a credentials helper file that will basically allow your system to shake hands with the Google Container Registry. So first thing I'm going to do is go ahead and bring Singularity in my path, the module load, and then we're going to run gcloud auth configure Docker. Okay. So, again, if you're doing this on your own system, you might have realized by now that what we need is gcloud SDK installed. So just keep that in mind. Now, I've already created one, so I may have a little bit different output than you, but essentially this should end up giving you a prompt whether or not you want to actually save this file in your home directory. It should go under home.docker/config.json. And now we can just run a Singularity pull. We'll do Singularity pull docker gcr.io. We'll give it the project ID where that container is hosted. So this is your GCP project ID. Then we have Python demo slurm GCP latest. Okay, so Singularity essentially is going to reach out to that container registry, and it's going to pull that Docker container over. And it's going to then convert that Docker container image to what's called the Singularity image file. So you might be asking, why the heck are we using Singularity? Why not just use Docker on this system? Well, Singularity it's really designed for HPC clusters. So if you have parallel applications, if you have applications that want to run on GPUs, they do have just some nice, easy to use flags to automatically bind mount device files for GPUs. It integrates nicely with MPI, provided the MPI in your host system and the MPI in the container match up. You should be able to do container runs across multiple VMs. So if you have thousands of cores you need to run on, it's pretty straightforward to do, which I'm sure if you've tried to do this with Docker, it is doable. I'm not saying it's not. Doing that kind of work with Docker is doable. It just involves a little bit more understanding of container networking and things like that. And if you're integrating with a job scheduler like Slurm, it's even easier. So we highly recommend it. The other benefit here is on shared resources. If you don't want everyone running around with root privileges, Singularity doesn't require root escalation in order to run those containers. So it ends up being a nice way to get your applications going without having everyone have admin or root access in some way. And then, of course, if we're using Google Cloud Build, you don't need root access to do that. Really, you just need your own. I mean, you could use your own workstation where it's safe to do so, and just use Google Cloud Build to create those artifacts. Now, the other benefit of using Cloud Build is, in that simple recipe we had, it was simply a just a build. So it's like, if that build passes, all it means is, hey, we're able to build it. But you can incorporate run tests, all sorts of other things down the line. All right, so it looks like our Singularity image file is done here. It's created. Okay, there it is. Let's take a look at this last batch file we're going to use. Test.singularity.batch. Again, make sure that account and partition are set to the appropriate values for you. And this time around, we're going to load Singularity rather than Python. And when we run our application, we're actually going to run all of our commands inside of a Singularity container. So we're going to do Singularity run. Give it the CIF file where we want to run basically the CIF file that's going to create the container for us, and then we're going to run which Python 3 inside that container, and then we're going to run our application. Now you'll notice that I'm actually referencing the location inside the container here. So whenever it reports which Python 3, it's going to report what's basically paths inside the container and not on the host system. Let's go ahead and run that. I'm going to refresh my console here, see what we got going on with the compute node. I was not fast enough today. So now we got another compute node coming up. Demo partition 0 has been taken down. So let's take a look at the SQ. We're in a configuring state. Let's take a look at sinfo. So demo partition 0 has been automatically powered down. So it's in an idle state, but this % sign means it's being powered down. So it needs a few minutes to basically catch up on the Slurm controller side to put it back in this idle tilde state. The tilde stands for cloud state. So it can be spun up. It's ready to go. So just like before, we're going to have to wait probably another 30 seconds here, maybe a minute. So yeah, let's. I guess while we're waiting, let me get back to just talking to you a little bit more about how you can use Cloud Build for like continuous integration. I guess by example, we have an application called Cell Fluids. It's a multi GPU fluids application, and most CI platforms out there don't already have the ability to give you multiple VMs. So I can't do the kind of testing I need to do for an HPC application where I need to run on like 1,000 cores or I need to run on 8 GPUs or more. So the one way to actually orchestrate that is to use Cloud Build to build your app, in our case, build Cell Fluids container, post it to the container registry, and then use Cloud Build to reach out to the controller over SSH to run the job, and then pipe back the logs to Cloud Build. So now I can get both build and run testing in one go. And of course I can actually test that at scale thanks to, Google Cloud actually has the resources to handle that kind of workload. It can certainly take a lot of pressure off of on-premise systems where you might be doing a whole bunch of work. Development, you could have some production work going on, and then you probably have folks doing like nightly testing, if not testing on every commit. It can really put a burden on-premise systems, and it can force developers into a place where they have to make sacrifices in terms of how often they test. I think we're all doing the best we can to have the best possible solution to keep our applications going. But I certainly prefer to test on every possible commit that makes sense. Certainly before I go to merge into like a develop branch or a master branch for that matter. Anywho, let's take a look at this job. Looks like we went through. And let's take a look at that test.out. So we got a few warnings. So these warnings, when you're running inside of containers, if the group IDs, are not the same inside the container as they are on the host, you'll get this warning about unknown group IDs. That's okay. It's benign. Which Python did it use? It used Python in user local, but remember that user local is user local inside the container, not on the host system. So it still ends up being portable, but now I'm not tied to this requirement to have a dependency on an NFS mount. SciPy, again, user local. NumPy, user local. Matplotlib, also user local. And again, all those user locals are inside the container, not on the host system. So I hope this gave you 3 good strategies to manage your Python packages. If you like this tutorial, if you want to share it with others, we have a code lab that will walk through all 3 of these strategies. Just check out our site, help.fluidnumerics.com/slurmgcp. You'll find some code labs in addition to other tutorials like creating these auto-scaling clusters and a lot of other helpful documentation to get you started with your own HPC resources. Of course, you can always reach out to us at fluidslurmgcp@fluidnumerics.com if you need any help. Of course, right now, if you have any questions, feel free to post your questions in the live chat. I'm ready to help you out with anything that might have been confusing today. Or if you have suggestions on things you'd like to see done on these tutorials, definitely just let us know. We'd like to make sure we're addressing topics that are useful for you and that help you be the best researcher you can possibly be. Of course, join us again. I'm happy you guys made it out today for our live stream. We do have our full schedule posted on our site again, help.fluidnumerics.com/slurmgcp. And underneath that, you can go to live community training. You'll have some information there on what we've got coming up next. We do these every Thursday at 4 p.m. Mountain Standard Time, Fridays at 9 a.m. And next week we've got for you, we're going to be looking at building OpenFOAM an OpenFOAM virtual machine image for Google Cloud, and we'll actually launch it on this FluidStorm GCP cluster. So if you're interested in virtual machine image baking in general, if you're interested in OpenFOAM, this would be a good tutorial to help you get more involved or develop a better understanding of Google Cloud Build and how you can use it for your applications and for your research. Thanks again for joining, and we'll see you next time.